Hello, this is a status report on what has turned into a month of doing three Arduino projects. And all three of them, I think, I will in the future be able to release to the public. One was this experiment that I was wanting to do with the true random number generator on an itsy bitsy. Basically, any Cortex M4, uh, the Itsy Bitsy M4, the Pi Gamer M4 Express, and the Pi Badge M4 Express. I have these three. They all have a Cortex M4, and there's a true random number generator on it. So I wrote the software to run an experiment. Can consciousness affect the bias of the random number generator? That experiment required something like multitasking. I needed a task that was blinking the LED, the onboard little red LED, at a rate to indicate how far you're moving the bias. So are you pushing it farther? Farther you push it, the faster it blinks. I needed a routine task to actually draw the random samples and display it on the RGB pixel, display the bias as a color on an RGB pixel. And I needed a task that was just monitoring for keyboard input so that I could control the experiment, like start trials and set parameters for trials. And then this would output a CSV file that could be later analyzed in a spreadsheet program. Well, the first version of that, I kind of hacked together that I would say in loop, is it time to blink the LED? Is it time to draw a sample? So I was drawing them once a second. Is it time or is there a key at the keyboard? And that was like, this is very old fashioned kind of programming where you have a main loop and you have like slots for your tasks. But, Arduino, I guess you could get RTOS for certain boards that are Arduino compatible, but I didn't want to install that. I just wanted to have coroutines, and they're not available. So a coroutine is a step below preemptive multitasking. What is cooperative multitasking? You the kernel of the coroutine kernel will launch a coroutine and it will execute until it yields. Okay, so it'll come to a point where it'll say, okay, I want to yield for some number of milliseconds. And then the kernel will pick the next coroutine, let it run until it yields. And as long as everyone's being nice about yielding control, then you get this apparent multitasking. But we call them coroutines because they're cooperating. I couldn't find that available in the Arduino library. You go in the library manager, nothing was available for that. So I wrote my own version of that, and this is something that I would like to release once I have it completed. But so I started off by saying, obviously, I need to play with the stack in order, give each coroutine its own stack, and the kernel would do stack switching so that when it wakes up a coroutine, it switches to its stack, lets it run. So everyone is in their own little stack. Well, I initially tried to do this all in C++, but GCC and G++, they are not happy if you play with the stack out from underneath them. So I had to turn to writing some assembler code. So, it was I was going to have assembler code anyways in inline assembly in C++. So all right, I'll I'll just write assembler code. So given that my platform is a Cortex-M4, I brushed up on my Cortex-M4 assembly language, and I successfully wrote a kernel, a coroutine kernel. Okay, and it's nice. Basically, to use it, you derive your class from the coroutine class, and that establishes it as a coroutine. And then you write a method called main, and main will be started, and main and its subroutines that it call can now yield control back to the kernel so that it can switch to another task. So it's very simple. You write a little class that has a little main method, and that gets executed as a coroutine. It was all very nice, but then I felt like I wanted to enhance my coroutines. So at first they were just able to yield for either 0 milliseconds or some number of milliseconds. And then I was like, well, I want it to be able to yield until, because I needed to know when keyboard input was ready. So I created a little call that says yield until a Boolean function returns true. And then what the idea would be, the Boolean function would check the keyboard or the serial port and check if a key's available, return true, otherwise return false. And so if I'm yielding until that's true, that function returns true, I wouldn't have to pull the keyboard, or I would apparently not be pulling the keyboard. You really are, but so I added that, and then I found that I want to be able to have signals, so a coroutine can signal another coroutine, and that was fairly easy to add to the code. And then I was like, hey, but if you're going to signal a coroutine, maybe you should be able to say, and by the way, wake that coroutine up because I just set as signal. So a priority wake up on a coroutine. And then I started having trouble because by the time I've added a few features in assembly language, it all had turned into some spaghetti code, and it was complicated in the branching. How am I going to do things? So I says, forget this, okay? I mean, I like programming in assembly language, but I need some assistance with some higher level structures. So I did the third thing, which I also hope to release, is I designed a high level assembly language. Okay, so basically it's a type of assembly language. It has, a model of having registers and address modes that you could use to load the registers, and some simple math operations, and procedure calls and returns and stuff like that. So a simple high level assembly language that also has if, else if, elif, end if. So a decent control structure, a while loop, an until loop, a case statement. And yes, I have go-tos. So I have a jump statement. So I wrote a compiler in Python that compiles this down into Cortex-M4 assembly language. And then, I use Platform IO, and then I wired that into Platform IO, so it's very seamless. You just write your code in this new language, and it gets compiled into a .o that gets linked into your project. When I did that, and then I said, okay, now I'm going to re-implement my kernel, my coroutine kernel. Wow, it turned out to be very much easier to write because I'm used to writing in C, right? Okay, so it was very much easier to write the kernel, to the point that the kernel, as it was, the assembly language version, was 650 lines of assembly language code. In this new language, when the assembler that it spits out, that actually gets assembled, it was only like 300 lines of code. So the code was more compact and modular because I had basically some high level constructs. So I was able to add easily this wake up feature, and so that's the state of that. My coroutines are working nice for Cortex M4. I use those to upgrade my experiment so that the experiment is using those coroutines. And so I've got one, the experiment is now ready for prime time. Two, I have a coroutine task switcher for Cortex M4, and I have a compiler for Cortex M4. Now, my original intent, the reason why I'm not ready to release those two things, the coroutines and the compiler, is because my original intent for that high level assembly language was it could target multiple backends. So, the initial target was Cortex M4, but it could easily target an ESP32, which is also a 32-bit processor. And with a little more effort, it could target an AVR, which is a kind of a mix between 8 bits and 16 bits. It's like 8-bit registers, but 16-bit address space. So I'm currently in the process. I had made it modular so that the back end is distinct from the main part of the compiler. So the compiler's in 3 levels. It's the syntax scanning level, and then there is closer to machine language level that handles dealing with registers and the mapping of registers to true registers or emulated registers, and the control logic, how an if statement is actually implemented in assembly language. And then there's a level of the back end, which is the actual assembly code that's spit out to implement all that. Okay, so I made it modular so I could plug in different back ends. I'm currently halfway through writing the AVR backend. I think I took that as a challenge because it'll be a harder one to do because of the 16-bit addresses and 8-bit registers. So I'm currently working on the AVR backend, and once that's working, I think then I will release that compiler as an open source GitHub project that people can use, and then I'll further develop to get it to the point where it's doing ESP32 also. And the coroutine, then at that point I'll release the coroutine library so that it will work for Cortex M4 and AVR, and then soon to have ESP32. I'll release that as an open source project, and already I'm ready to release the experiment itself as an open source project because I don't need to, I could just put the assembler output from my compiler into that project so that it can be compiled right now for an itsy bitsy. I mean, that's not a generic project. That's specific to a Cortex M4 because it knows how to get random numbers from a Cortex M4 true random number generator. I did make that experiment more generic that it'll also run on a Pygamer. So Pygamer doesn't have it has a different type of RGB pixel, but I was using it has a big, I think an OLED display, and I was using it as the color output. So that experiment is ready to be released, but it's also ready to be run. And I've played with it myself, and I get some possible signal in the spreadsheet that I may have caused, may have had an influence, maybe not. I need to do now some rigorous experiments. The way that runs now is I enhanced its output so that it used to just print out the bias as a number, while it was also displaying the bias as a color. And so the intent was, during an experimental trial, you try to make it more red or more blue. You'd say start trial, it'll tell you, what to go for, more red or more blue, meaning more ones or more zeros. And you'd watch the light and the little blinking light to see as a visual feedback. Well, I also added some graphing capability. So at the terminal, with the terminal emulator hooked up to the USB serial on my laptop, it'll do an ASCII graph. So it'll have a little chart recorder running up the screen. So as the bias is wandering, it's a line being charted, scrolling up the screen. So and I'm finding that gives me some more immediate feedback as to how the trial went, as opposed to trying to load the whole thing into Open Office and make a chart and then analyze, like put a trend line and all that kind of stuff. Basically, I can look at the TTY chart recorder and see, is it running stable? Okay, let's start a trial. And then at the end of the trial, since I have 2 minutes of time on the screen, I can see if I swung the bias in the direction that I tried to swing it in. So that's all ready to actually now run trials. And I have a friend who I have lunch with that I've been talking to him about this stuff, and he's excited about it. And we're intending to do joint trials where I get ready to do a trial, and and the plan is I'll text him, okay, we're going to start a trial in 5 minutes, get ready. And then when we're all ready, I say, okay, let's go. And we're going for, we'll get in, what are we going for? We're going for red, let's say. So we're going for red. And then we'll use our so-called mental powers to influence the random number generator to go for red. And the idea being, can two brains work better than one brain? So that would enter into the types of trials I would do. A trial with me alone, a trial with him alone at a distance, a trials with us together. And then while I was preparing for this video, I was like, hey, we could do, because I have the ability now to do live streams on YouTube. I could live stream this experiment and do a worldwide, though I don't get a lot of people on. I could do a worldwide kind of experimental trial where we all put our brain power together to try to influence the random number generator. So that's the state of it. I'd like to release it because, these itsy bitsies, they're not a lot of money. They're like $20 or less dollars on the Adafruit. It's their board on Adafruit's website, and all you need is my software, and you can be running trials yourself. Oh, okay. you have to add some components. So I made it a little more elaborate. Because I want to get CSV files out of it, the Cortex M4 has, or at least the Itsy Bitsy has some space for a little flash drive on it, but it's not big enough. And so I added I don't know if I mentioned it in another video, I added an SD card reader to it's on a breadboard now. So I added an SD card reader so I could write in large CSV files, comma separated value files, if you don't know what that is. And right now it's running and it's just spitting it out, and I can look at historically over the last few days, how has the bias been going, right? And then it was like, well, but I want to know the actual time of day of each sample, which I'm taking one sample a second. And so I added a real-time clock module to it. So it's a nice little battery-backed up real-time clock module. It uses a rechargeable equivalent of I think a 2032, but it's the rechargeable equivalent of that. And it keeps it charged, and when you disconnect the power and put it back, it loads, it initializes with the current time because it's kept on the clock. So my CSV files are time stamped with the date and time down to the second when the sample was taken. So others could build that. It's very simple to plug these components together. I think they're both using I2S. I think they both use I2S. I don't remember. Maybe one is using, no, maybe they're both using SPI. I don't remember. It's been a while since I put it together, like several weeks ago. I've been working on these other programming projects. So I'm going to switch gears and not be coding for 16 hours a day like I've been coding, and relax a little bit because things are kind of working, and get into actually running the experiment. And so there will be more videos about how that experiment is going, and like I said, potentially a live stream where we try to do this live with lots of people. And I'll be getting into how to release that project, the experiment project, on GitHub, with instructions and how to wire up the components, and and having the software on GitHub. It's already on GitHub, but it's in a private. It's in a private repository. But I have to write documentation for people. So that's the status. So a lot has happened in about a month. I haven't been doing any YouTube videos in that amount of time, and I hope I still have people that want to see my videos after such a long lapse. But thanks for listening. This has been, looks like we're up on getting close to 25 minutes for this video. If you got this far, thank you for listening all the way to the end. And we'll have more in the future.